Yeah, we can hear and see you.
Okay, yes to both.
Good. Thank you. Okay, the first one. I will be sending an email about this. Everybody should return the caliper and the part. And the date I have fixed is the 17th, which is next Monday. 9:30 to 11:30, 1:30 to 3:30. Come straight to the lab and return it. I want to be around, so would be Dave. It's important that you return them before we end the term. I hope nobody has a conflict. Uh, Hopefully the weather is not going to be as bad as what it is right now. Number 2, I'm almost done with project number 2 evaluation. I would finish either today or probably not today, tomorrow. Then I'll have to compile everything and send it to you by email. So you will get a feedback before the end of this week. That's on project number 2. Project number 3, keep proceeding. This is what should happen. When you are ready, you must get it tested by Matt, and I will also be there. Matt would be correcting this project report, so he needs to see your final solution implemented on that digital board so that he has less work to do. Your project number 3 report is due on January 19th, which is one day before your exam. We have very little time to go over because marks are due. Student records is pushing. So make sure everything is done. There are no extensions beyond January 19th. Final exam is on January 20th, and it is online. 4 p.m. is the starting time, and the university has forced everybody to go only 2-hour exam and not 3. Normally, this is a 3-hour exam. Okay, I have not gone there yet. This weekend I will finish, and I will give you some kind of a feel as to how it's going to go next Tuesday. Then the last one, I've now got the wording or rule for CIMA 2 to be online lectures and in-person lab. Okay, currently there are 2 students registered in CIMA 2. The maximum I would take is at this time, it is 2 more or 4 more, depending on, there are 2 lab slots, BO1 and BO2, 3-hour long. It cannot be done as a single person lab. It has to be in groups. Traditionally, it's been 3. Last summer when I offered it, it was 2 people in a group. Okay, so if you wish to take it, let me know. You have to send me an email. Okay, because I would be very soon finalizing the details of how the lab is going to run. And what else? I guess that's about it from me. If you have any questions, I will send an email about the return of caliper and the deadline, as well as send you individually your project 2 evaluation sheet. Okay, any questions? Okay, now let's proceed. I have only a few more slides on this section. Then I will be showing some video films on robotic applications. Let me move this little stuff out. Okay, When we talk about robotic application, it used to be dominant in the auto industry. Not anymore. I'm not saying auto industry doesn't dominate in robotic applications. There are a lot of other people who have now implemented robotic solutions. Quite a few have based their solutions on laser and vision based guidance. Now, something that I used to cover, but I do not have the time anymore, is when you talk about robots, there is a class of robotic applications that involves automated guided vehicle, AGV as they are called, where you have a robot that is mounted on top of a guided vehicle, and it can go to different areas in the shop floor, fetch parts, deliver parts, or move parts, and they have got their own program built in, and they will follow. There are different ways of following the path, either reflective tapes or buried cables through which electromagnetic coupling takes place. And they also work on the basis of GPS. So there was quite a number of applications. Majority of application involving robotics has been in welding, grinding, deburring in manufacturing applications. And as I said in my last lecture, glue operations in the automobile industry is also picking up. Now, you are going to see in the video how the food industry has picked up quite a bit in terms of application of robotics. Okay, I don't want to talk about it. You will see it on the videos. Metal casting, drilling of holes, substituting what a CNC machine will do, nut and screw driving in assembly, very standard application for robotics. They all benefit from the use of RCC, remote centered compliance, which I talked about in one of my earlier slides. And RCC are also reaching a very high level of sophistication. They have built-in sensor technology which can determine the three components of forces and the three moments in X, Y, Z direction, fully instrumented, which can be fed to the robot controller, provided you cooperate, or the instrument developer and the robot people collaborate in making this happen. There's also lots of vision-based companies who are making machine vision. One of the popular brand is Keyence, who make all kinds of other instrumentation too. I'll talk about some interaction with Keyence on a project that I finished about 4 years ago. Parts handling, transfer, and palletization. Palletization is a word that is very commonly used in robotics. No, in automation. Palletization is stacking row by column on a wooden pallet so that it can be wrapped around and sent to the shipping for distribution. So robots are capable of doing palletization with the programs custom written. Punch press. You don't want to have a human working on a very heavy duty punch press, which can generate a fair amount of forces. So robotic loading of punch presses is also a common automation application. Loading of ingots into hot furnaces before forging is again a standard application. Now, something is not mentioned in the notes. Siemens has a jaw. I wouldn't say mechanical jaw. It is mechanical and electrical combination. What it can do, if the CAD can program the gripping positions of the robotic gripper. As the part comes out of the furnace, it can automatically press on the part. It's almost like pressing on a hot ingot to almost form the shape of your final product and then cut it. So that minimal amount of work is done in turning it or milling it to the final product. So Siemens has one of those in place. Robotic applications are also benefiting and will also benefit more by force and tactile feedback. They can compete with human. Human has powerful tactile feedback in multiple fingers. Okay? So a lot of instrumentation is being developed in this area to help automation benefit from that kind of a sensor technology. Electronic industries use it quite a bit in printed circuit board insertion and development. Last night I was watching a video. Maybe most of you do not know that I am a heavy duty hobbyist in model train, and not the traditional model train. All my locomotives are DCC, that is digital command control equipped. So you can program them to do all kinds of things. Now, scale trains in California showed me 38 minutes of how the model train by them is being built. Okay, where they use all kinds of automation that including the controller board that goes inside the locomotive, which is very, very small because the locomotive itself is small. I do HO and N combo, 1:87 and 1:137 is the scale. And if you can imagine boards that can produce sound of the locomotive as well as control many parameters of the locomotive to be put inside the shell of the locomotive, you are looking at micro machining. So they showed how robotics, CNC machines, and other kinds of automation are used in developing the scale locomotives and scale rolling stocks. Part sorting, again, you will see it in the videos used extensively by food industry. Now, what is picking up very rapidly is machine vision based applications for robotics, because robot, like human, don't have a tactile feedback, don't have a vision feedback, but if you can give them the vision, then you can do much more. I won't say it is new, it's been there for about 15 years, but more rapid applications are coming up. For example, if you look at the GoPro 10 camera, you can do 4K easily, you can do 5.1 or something like that, they call K easily, with a 23 megapixel camera, and it is so tiny. Okay, so you can imagine what the electronic industry is developing in terms of vision. Okay, so automation will benefit out of it. Applications in food industry, again, you will see vision-based applications is extensively used. So where is the development thrust that is available? Future applications will rely on development of software that is going to integrate low-cost sensors with low power but highly capable processing. software, hardware to work with this sensor, because you're looking at a smaller footprint of robots working in a tighter environment where you can't let the robot's hardware occupy more space. Okay. Shape memory applications in automation is also there. How many of you know what a shape memory is? Either one of the material science course, I hope.
I think is that the one that when you heat it, it goes back to its shape or something?
Yes. Where was it covered?
Where was it covered?
Yeah, which course?
I think Doctor. I think Stress talked about it a bit.
Oh, okay. Okay. Does everybody else know? Okay, I don't want to go. It is actually a fairly big section by itself. Shape memory alloy has the property that if you heat it, I would say by 20 degrees Fahrenheit, let's say from room temperature, which is, let's assume, is 68, and you push it up to 90, 95 degrees Fahrenheit, the alloy will contract, not expand. So if you take a guitar wire 1 meter long and heat it by 20 degrees rise in temperature, depending on what it is made of, it'll expand in length. The shape memory wire, let's say 10 microns in diameter, if you heat it by 20 degrees, a 1 meter will contract by as much as 14% of its length. So if you take a 1 meter, you can almost see a displacement of 14 centimeters contraction. As a result, it works like a spring. Not only that, it can carry load. So if you make a bundle of this wire, you can increase the load carrying capacity of these wires. The application started as a result of its use in space exploration. The solid propellant booster rocket motor, which propels the capsule above, is the last one to separate. Okay? How do they do the separation? They use shape memory alloy applications, which literally, like a boa constrictor, allows the separation to take place so that the solid propellant shell will dislodge itself. Okay? Now, in the area of robotics, because of its compact size, you don't have to take a 1 meter wire. You can make it into a coil and heat it up by passing electricity through it. It will generate quite a bit of force compared to its size. I have done, I'm not doing it now, a couple of MSCs. I started using shape memory applications and several science fair projects with me and my son took place, and we developed a lot of engineering applications using shape memory alloy and wires. That's where I got into the system. Now, the other application of robotics is also going into a lot of medical applications. If you look at the MRI board, I hope nobody has gone through a board. I have not gone through yet. Hopefully not. Computer-aided tomography, they are all using robotic-like devices. Like when you talk about MRI bore, you go inside the bore on a platform, and then either the platform displaces or the bore displaces and rotates in order to scan your body. It could be a specific section or the whole body scanning. So that's where the robotic application started. Now, laparoscopic surgery, non-invasive to some extent. I already talked about how robots are not going to displace surgeons. They are very accurate, but body inside moves around. So you don't want to mess around and cause a very precise device to deal with a device that moves around. Okay, DNA coding. One student who took this course 20 years ago, his hometown is Winnipeg. I've not seen him over the last 5 years. His parents used to live here. So he worked, I hope he's still there, in Texas, Dallas, where the company that he was working for were involved in DNA classification and coding. It used to take close to, according to him, about 20 hours using old technology. Now robots are being used to come up with a very rapid classification of almost 1/100th of the time it would have normally taken. So again, medical application. MRI I've already talked about. Underwater applications, there are a lot of devices that go quite deep, and they have arms that are attached to them to go do some scanning, examine, whatever, quite deep, where humans don't really want to be going for too long a period of time. Mobile firefighters, well, a lot of police department, firefighting department use robotic-like devices which can be launched to examine, extinguish, or combat situations using devices, and the military also is quite a bit interested. In the old Iraq war, the US Army employed a lot of such devices because that time it was the chemical warfare that was being considered as a major threat. So these kind of vehicles were launched. Now, cleaning of ships and aircrafts. Whenever an aircraft comes to your dry dock, and these days the container ships are becoming bigger and bigger and bigger, and when they are underneath the water for let's say 6 months, there is a lot of scale that forms, which affects the fuel efficiency of these ships. Same thing applies to aircrafts. We don't see the dirt coating on aircrafts quite often because they are flying at 450 or 500 or 550 miles per hour. But they do cause, any coating on the surface will cause some turbulence, which affects fuel efficiency, which acts as a deterrent for flight stability. So aircrafts are cleaned, but when you look at the ship and the aircraft, do you take a mop and a brush and clean the whole stuff? Especially ships with the scales, you got to descale them. So robotic-like devices are used in by some industry, not all, in cleaning of ships and aircrafts when they come for inspection. Bomb disposal, battlefield, minesweeping, and artillery loading, these are all I'm not going to say they are robots, but they move like robots. Okay. Robot tailors, you want to pay $1,000 for a jeans, custom developed, custom stitched to fit your contour by computerized machines. All that you have to do is stand on a revolving table and cameras scan your body and take measurements, supply to the controller, and bang, you go. You get within 1.5 hours. Where does this happen? Japan. The problem is you pay $600. You got to maintain your body to fit into that jeans or whatever. Otherwise, you wasted your money. Tree climbing robot. Well, this is something that BC, British Columbia, was very much interested, and they do have something going. Basically, when they want to cut very tall trees, well, if I can launch a vehicle from ground, which will negotiate the tree branches as well as chop them and bring them down slowly and steadily, well, you don't need to worry about human getting injured. Well, I do have a machine in my house developed custom, which will climb poles like a monkey. Again, I did this work with Nish when he was in school. Then came hydro power line repairs and de-icing. Typical in a very cold environment like Manitoba, where during winter time we have a lot of ice being coated on power lines. And then with the wind, they start galloping. And that's when they break down. The wires break or the tower collapses. Millions and millions of dollars gone in terms of repair. So Hydro was very much interested in a de-icing robot. In fact, the two of us developed a robotic device that will go, but Hydro had put the money somewhere else to fund somebody else and got nothing out of it. And that's why the hydro power line repair kind of a project got into MEC 2112. Okay. Applications in space research. Well, these days there is a lot of interest in going to Mars and the moon and working in the outer space. There's a lot of devices that are required to launch, like Canadarm, to launch satellites or move debris or get rid of debris that may come and collide. So there is all kinds of applications out there waiting to be grabbed. Then there's a class of machines which mimic creatures, insects, human beings, and they are called biologically inspired machines. And the design is based on duplicating what a snake does to move around, or a leech, or earthworm, you name it. They all move using all kinds of different ambulations. So the biologically inspired machine, which is also called the biomimetics, is a fair amount of work that is being explored in this area. In fact, I have about 10 hours of presentation on this aspect, but again, it doesn't fit with this course structure. Now, I talked about cleaning of the hull of a ship. This is way back 30 years. Archive, copy, black and white. Now, this is a French invention. So the principle is what is important here. So what you have here Oop. Yep. Yes, my pen writes. What you have here is a wire brush which will spin with the motor here. Okay. Now you have underneath here a magnetic clamp, and you have suction cups here. So these two can alternate or can be gripping the metal or whatever at the same time. So because it's got magnetic gripper here, obviously non-ferrous metal application, you have to come up with something else. So this is what will happen. Let's say the vehicle is grabbed here and here at this location. Then you start spinning this. It'll clean this area, and it's also a boom that can move or rotate so that you have a sweeping surface here that it'll clean. Then you take the suction out, keep the magnetic clamp, reposition this here, okay, and then clamp this and reposition this here. You will start propagating in this direction. Okay, so instead of having a human do all those jobs, you have a robotic device that can do the cleaning or deburring or descaling, whatever you want. So even though the concept shown here is pretty old, all kinds of newer ideas have come up. Okay, now your carpet cleaner these days, and now they're talking about snowblower, which is going to be guiding by itself. I wish I had one right today. I have a lot of snow piled up all around. So more and more are going to come. Roomba is another application. There are so many different levels of Roomba with so many different intelligence. Okay, so they're all robotic devices. You program it and it moves. Tall skyscraper cleaning. Don't need people to be hanging on ropes, on paddles, and start cleaning. You can have devices that will clean the surface. Now, in the robotic applications, nothing is more important than what goes as the end of arm gripper. It's called the EOT, end of arm tooling. Okay? Now, I constantly talked about handling sandbags, salt bags, cement bags, whatever, 25 kilograms. Now, here is an application where a sandbag is posted somewhere downstream here, away from the scene of action. Let's say somewhere here. As you see now, there are a lot of bags here. Somewhere out, further out, it is being filled and sealed, and it is finally transported into this conveyor. And you want to take it and start putting it somewhere else. How would you grab the sandbag from the conveyor? Here is a neat idea. Okay? So you see here scoops cut on the conveyor, and you see these fingers, many of them. There will be similar set on the other side. So when you actuate this gripper, these fingers will go hug the bag and their end will go underneath. So it's like grabbing with the multiple fingers and then lifting it, because the stability of the bag will not allow putting suction cups or whatever other type of grippers on top to lift it. So here is a device commercially available to handle that type of flexible material that is being packaged. Now, again, you're going to see some of these in the videos. Here is a big box, whatever it contains, that needs to be lifted, and it has already come packaged. 1, 2, 3, 4, 5, 6 suction pads. Why 6? Because it's a long, you need stability. You can't just grab it in the middle. Okay, so it will develop uniform force, and then you can lift it up, move it wherever you want. Again, innovation in end of arm tooling. This is very different with respect to this type of application. Okay. Now, here is a panel which is fiberglass and is being worked to trim it. Fiberglass, whatever, you don't want humans in the loop. So this end of arm tooling here will allow it to trim the panel after it comes from somewhere else to the precise shape, a robot application. Now, this, what is shown here, is a spot welding application. Now, in the case of a spot welder, you have the panel held in a fixture, so you don't move the panel. You move the robot arm with the spot welder, which looks massive, and then go and spot weld wherever you want. Okay, so the payload is carried, rather the payload is consumed by the spot welding gun that is attached to the robot, because it doesn't have to carry any other load. Okay? Now that's the another view of the spot welder. You can see how massive it is, and you can also see the parallel arm configuration, articulated configuration robot used. Another view of the robot with the spot welder. It's made by KUKA, and I have a KUKA in my lab, and this is a Nachi, which doesn't exist anymore. That company has become something else. Basically, why I brought this slide is to show the massiveness of the end of arm tooling, and they don't need to carry any load. They move to the workplace. Now, soldering and desoldering in electronic industry can be combined by using, in this case, a SCARA configuration robot. This is the end of arm tooling that will do the job of solder and desolder. Okay, painting, very standard application you are going to see in my videos. Printed circuit board population. Here I have a SCARA configuration doing the job. Okay, I think I mentioned about this. Robot can be hung upside down, but if a robot is designed to be put on the floor, you don't hang it upside down. There are some parameters that have to be changed, some mechanical design that has to be changed, but it can be done. It increases the work envelope substantially. Okay. Now, here is a case where all that I want to do is to pour glue all around here on a contoured body. So this is my glue gun, and you program the machine in whatever way you like. It'll accomplish the job without any problem. Plus the quality of the size of the bead is going to be pretty repetitive, consistent, as opposed to a human doing the job. It's like caulking. If you want to replace your caulking on your tub because it's been old and it's mildew deposited, well, you try caulking for the first time, you're not going to like what you did. But with experience, you will gain there. With the machine, no need to worry about it. Now, this is another application that is pretty powerful in the area of robotics. Deburring. That means if I had sharp edges all around from molding or whatever, forging or machining, and I want to clean it off, robots are the best tool. But remember, robots are very stiff structures except Scarab. Okay? And stiff structure and deburring don't go well, because you have a deburring tool which is a grinding wheel, and you attach it to your motor and you take it around. The deburr may not be uniform. This is capable of very accurate placement. This actually tells you what would be the difficulty of robots being used in surgery. Here, I have to feel the force that I exert here and adjust. Plus, this grinding wheel is also going to slowly and steadily wear out, right? So I must perform compensation. So if I get a force feedback, okay, from the this device and interface it to the controller of the machine and apply constant force by compensating the end of arms position, well, it's a much better proposition, right? That's exactly what you would need. And to talk about just the word force feedback, it's not as simple as what I'm telling you. This is from a control perspective. You have to do the model. Okay? So again, I do this in the graduate course. Now, I'm not going to go too deep into the actuation because I do it in SEMA 2. When you take the robots, we talked about hydraulics, pneumatics, and the electric as being the actuators. Hydraulics can be used either as a linear actuator or as a rotary actuator. And the principle of hydraulics is pumping oil through a piston and a cylinder to extend or retract. So if I had a hydraulic cylinder and a piston extending, and there is a port here, and I have an inner cylinder on which this piston is moving, and I have another port here. If I send oil pressure here, obviously it displaces this way. And if I send oil pressure, it displaces this way. Now, if I put a control valve here, where I can control differential pressure across this, oil being incompressible, I can maintain some position control in the case of hydraulics. This can be done for linear or rotary actuation. I can also get feedback, position feedback of this cylinder's extending and retraction position and develop more. But hydraulics, the problem is you have oil in the system, right? And this pressure could be 3000 psi, very high pressure, to carry big load. Oil, high pressure, flexible hose may not be good for some application. Like, if can I do welding? Well, would I do a welding with a hydraulic robot? The answer is no. But because it's fire hazard. Plus, if I want to lift very heavy load, yes, hydraulic will come into play. Position control is possible. Extremely high lifting capability can be had with the hydraulic systems, far more than the other two that we will talk about. The pneumatics is very similar to hydraulics, except instead of oil pressure, you use air. And once you talk about air, we talked about it in the last lecture, compressibility starts coming into play. So you can't really model to bring it to an intermediate position with the air on this side and air on this side and a load W or force that is going to come in this direction, counteracting position. So what would be the compressibility of this air? How does it come into play when the force comes into play? Well, anything is mathematically possible, but to implement it is another ball of game. So, but if I'm looking at bang bang controller, as I said in my last lecture, move from a home position to an advanced position and stop and stay there. This will do it. But it does not have the capability of carrying as much force or capable of carrying, not carrying, delivering as much force or ability to carry big weights. Pneumatic will not be there. But extremely fast. From here to here, within a matter of 1 second, at a distance of 10 centimeters, 20 centimeters, a meter is possible. Because it's a function of how well the cylinder is built, what is the friction, what is the o-ring that will be used, and the magnitude of pressure that you're going to apply. Okay, different loads can be lifted with a different by varying the pressure. Like in SEMA 2, most of the applications will be centered around 30, 20 psi, even though we have about 90 psi available in the university's air supply. Then comes, again, pneumatics can be linear or rotary. Then comes the electric, which is the most common. All that you're doing is using electric motor, which could be servo DC or servo AC, or could be stepper motor, or could be digital servo, or could be linear motors. There are so many different types. They need an interface, they need programs, they need control models. Unlike these, this is going to involve more complexity, but will give you a different level of sophistication. Electric, in comparison to hydraulic, will have lesser load capability compared to hydraulic, because you can't keep on increasing the size of the motor. You can't put a motor that normally is used in your elevators to take people carrying capacity of 1,300 pounds or 1,500 pounds, and you have a huge motor sitting at the roof. You can't put 6 of those in a robot and say, well, I can lift. The robot will not even move because the different links are at different lengths, and you can't put the motors at the end of the links. Okay. So this slide, in a nutshell, tells you hydraulic high weight to power ratio and higher speed. Primary use in large robots with high payload and usually parallel arm configuration. And this is something I did in the Bristol Rockwood plant of dealing with the hydraulic robot, but there were many issues that had to be solved. Electric drive speed and power limitations will start coming in, but they are very accurate, have a good repeatability, and the control can be simple or complex depending on the application. Okay? Pneumatic, ideally suited for pick and place applications. The least expensive and the best for PLC application. Do not have the proportional control aspects, which means I can go to an intermediate position. Okay. Feedback to position monitor position and velocity will not work with pneumatics. There is no such stuff. Precise control of position, the answer is yes, because you're driving it against a hard stop and you're retracting it to a hard block stop. Oh, that's the end of this section. Any questions before I open up my next presentation? Any questions? Nope. Okay. Now I hope my video will come up. Oh. Do you see anything happening in my screen?
I see just a gray screen with your mouse on it.
What do you see now?
Still nothing, Professor.
Somewhere it got closed. Okay, let me get to it. Just give me a few seconds. In the meantime, you can ask me questions if you have any.
Actually, I have a very quick question on the last slide.
Yep. Go ahead.
All of the properties that you showed there, they were for pneumatic control only, right?
Let me see whether I can. It says I'm sharing that slide. Everything has come to a stop. Okay, what was the, what did I put on that slide for pneumatics? Your question, let me understand. Is the last slide pertaining only to pneumatics?
Yeah, yes.
Yeah, what did I say in the last slide?
Like some properties.
Yeah, okay. Proportional control, not possible. Yeah, that means that's for pneumatics. Both hydraulics and electric can do it. Okay. What's the second one? You said there are
Feedback, is that possible?
feedback. Well, the cylinder is going to move from home to an advanced position, right? Air pressure is going to apply on one side to make it go to the advanced. Now, can I apply differential air pressure with a difference of 1 psi to hold into an intermediate position? The answer is no. Okay, unless you come up with a lot more complex feedbacks and so on. So it is not worth it, because then you shift to another form of actuation. So yes, proportional control aspects does not happen with pneumatics. I would say whatever I did on that last slide pertains to pneumatics.
Thank
Yes.
you.
Okay. Now, let me check where I have lost. I am going to go back and open up again. If I lose you, my voice is still coming through, I think. It should say I'm already up with the... Okay, I'm back in WebEx. Now it's probably going to say I have multiple launches. Tell me I should be able to join my existing session. Host. Okay.
Hey, Professor, we can't hear you.
For now. Something else. Can you hear that
Yeah, you're good now.
with echo?
Yeah, we can hear you, just still can't see the screen.
Wait. On the Thursday lecture, I'm going to. Okay, I get a. Okay, I get a lot of feedback. Can you hear me now?
Yeah, except there's still some feedback.
Oh, wait.
Yeah, that's good now.
Thursday, I will show you the video films. Then I have one section in PLC to wrap up. I will finish that. It probably is going to extend to the next week. And I think that's where I will stop. Okay. So please show up for the next two lectures. I'm going to come.